Okay, good morning, everyone. So I'm very happy to say a few words in the introduction of this webinar on AI for healthcare. So, this webinar, so this second webinar of SudParis is, now there are regular events of SudParis. And this is the occasion for me to say a few words about the recent events and activities of SudParis. So we had a very successful hackathon a couple of weeks ago, which gathered more than 200 students. And it was organized with the help of our corporate donors, which are L'Oréal, Capgemini, Total, Rexel, and Kering. And it was also a very successful event in the sense that all the topics and all the material, all the data was also planned and built together with our corporate donors. And the topic was AI for energy efficiency. And the other major activities of the center was to go on with recruitment of top-level professors, and we had a number of recruitment at HEC and IP Paris on various topics of AI and data science. We have also a very successful fellowship program which received a high number of high-level proposals from researchers of HEC and IP Paris, and we are currently under the phase of evaluation with our scientific advisory board. We have also received a high number of PhD grant proposal or submission, and we are also in the course of evaluating these proposals to allocate a number of PhD proposals on the fund of SudParis. And also, I also should mention also the entry of INRIA in SudParis, which is also a very nice very nice news for SudParis. So let me stop my introductory speech right away, and so then we can jump into the webinar. And Anne-Laure, if you want to go on and present this very exciting program of introducing our speaker, Anne-Laure.
Thank you, Gaël. Good morning, everyone, and welcome to our webinar on artificial intelligence in healthcare. My name is Anne-Laure and I'll be co-hosting this event with Sylvain Lecorf. This morning, we'll be listening to 4 research presentations, each lasting 15 minutes. These presentations illustrate the research on AI in healthcare that is currently ongoing at SudParis. Following the presentations, starting around 10 o'clock, our researchers will be joined by panelists to discuss the research presented, as well as the challenges surrounding AI in healthcare going forward. We'll only discuss for 1 hour. It will go fast. You may ask our researchers and our panelists questions throughout the event. If you have questions you would like to ask the researchers during their presentation, please use the Q&A function that appears at the bottom of your screen. Please do not use the chat throughout the event. We'll only be using the chat for technical issues should they arise. The researchers will reply to your questions in the Q&A space after their presentation. If your question is more general and better applies to the panel discussion, my co-organizer, Sylvain, will be asking it as part of the panel discussion. Please note that you may upvote a question that was asked by someone else and that you would like asked as well. We will seek to address all of your questions to the best of our ability within the little time we have. So let's get started. Please join me in welcoming our first speaker, Catalin Fetita, professor at Télécom SudParis and the head of the Media team. Catalin, the floor is yours for 15 minutes. I will give you a signal when you have 1 minute remaining. Do you want to share your slides?
Yes.
Thank you and welcome.
Everybody see the slides? Okay. For the introduction and for the invitation, in this talk I shall discuss the application of AI models in quantification of lung lesions in fibrosing idiopathic interstitial pneumonia and potential extension to COVID-19. So fibrosing idiopathic interstitial pneumonia, it's a subclass of infiltrative lung diseases leading to fibrosis in a continuous and irreversible process of lung function decay, which requires regular quantitative follow-up with the CT to assess these lesions over time. On the other hand, COVID-19, it's an alveolar interstitial pneumonia, which is suspected to evolve to FIP in 10 to 30% of severe cases. There are some differences with the FIP concerning lung lesions in COVID. That is the preponderance of ground glass regions in peripheral lung, less or no amount of fibrosis in the lung, and in the severe forms, there is presence of consolidation similar with another disease, acute respiratory distress syndrome. So to have a better insight on the pathologies that the appearance of these pathologies on the CT images, here there are some examples of disease patterns. So the fibrosis appears as dense reticulations in white surrounding small air regions. It is appearing mostly in IIP. Ground glass present in IIP and also in COVID shows as hazy opacity, sometimes including reticulations. Emphysema, present in IIP and in chronic obstructive pulmonary disease, shows as low attenuation regions due to alveolar sac destructions, whereas consolidation specific to COVID-19 represents dense regions, mostly in the lung periphery. So the objective of this research is to develop an automated system for a quantitative follow-up of this type of lesions using volumetric CT with applications to different type of disease. The idea is to have a solution able to process the entire lung volume and provide the lung region partitioning into defined phenotypes, normal and lesion. The analysis model will be based on deep learning and more specifically on convolutional neural networks. So the challenge to overcome by this model, it's mainly related to the ontological overlap between classes, as shown here in the bottom row on these images for the different patterns encountered. And this overlap being even more reinforced by differences in CT acquisition protocol. So the classification problem can be tackled as a 4-class problem or as a 3-class problem by grouping together the fibrosis and ground glass in a new class called or denoted by IIP. So this is what we will do in the following, and the remaining of the presentation will discuss the materials and method used. So namely the building of the image database, the model selection for FIP analysis, concerning 2 architectures involved, patch-based and end-to-end, and also some details on data preprocessing and training strategies. We will see the comparative results, and finally, I will present how the retained FIP model can be transferred potentially to COVID-19 analysis. So the database was built at the Avicenne Hospital, was collected at the Avicenne Hospital in Bobigny, which is a reference center for infiltrative lung diseases, with a particular care in ensuring a similar image quality despite slight difference in CT acquisition protocols and even in scanner type used. The database was annotated by 1 expert and 3 junior radiologists on a basis of 10 images per case, 1 case including about 400 actual images. So we finally achieved 56 cases with ground truth available, but this database shows a large imbalance between the classes that we have, as shown here, with the less representative classes being the emphysema region. Also, there was a highly variable occurrences of classes from patient to patients, meaning that we had to perform careful split between training and validation sets during the training. So 2 CNN architectures were here investigated. The first one was a patch-based CNN, where the class of a single pixel is determined by a small receptive field around it, called a patch. So we look here at a deeper version of a texture CNN introduced by Antimopoulos and colleagues. And the second architecture is an end-to-end fully convolutional neural network that performs the classification directly on the whole image at once. Here we look at a simplified version of UNet architecture, with expected advantages here being the processing speed, but also a higher contextual information for the decision. Concerning the patch-based CNN, because of the small receptive field for the inference, there was a possible bias that could be introduced by the normal high densities of the vascular regions in the lung that could be misled for fibrosis. To avoid this, we have introduced a pre-processing step consisting of a removal or a highly attenuation of the vascular opacity through the lung, as shown here. This was applied for both architectures before the training. So concerning the training step, first the class balance in training and validation splits was ensured by patch selection in patch CNN, but it was much more difficult to achieve for the end-to-end architecture because here one sample is one image itself. So we need to compensate this in the loss function, and for the optimization part, we use for both architecture stochastic gradient descent with momentum. The loss function was cross entropy for patch CNN, but for the end-to-end CNN, the loss function was chosen between among several possibilities to ensure to compensate for these unbalanced classes. So cross entropy was not a good choice, leading to over prediction of some classes. So we look for some weighted versions of cross entropy, linear, log weighted would perform better, and finally dice that has also an advantage to not to introducing additional hyperparameter to be tuned. So finally dice loss was retained in this case. We furthermore investigated the possibility to discard the pre-processing step with vascular prefiltering because it's a quite long process. And for this, we we have to change the optimization scheme in terms of dealing with the learning rate schedule. Indeed, for classic progressive decay of the learning rate over the time, the training applied on the native data set did not predict at all the emphysema class, as shown also here in the green curve for the accuracy of the emphysema. So a solution consisted of replacing this progressive decay of the learning rate with an oscillatory scheme in a triangular shape, and the same thing for the momentum. So this is the learning rate and the momentum that allows to start predicting the emphysema, again, the green curve here, and the blue regions in the image. So a comparative analysis between the two architectures with the different training strategies showed that the end-to-end CNN with dice loss overperformed the patch-based CNN, but also that there was no performance degrading when working directly on the native data using the same model with the triangular learning rate schedule. So this was the final architecture selected for end-to-end CNN. And here are some qualitative examples of prediction for with the patch-based and end-to-end CNN. This is an obese patients showing that the patch-based CNN misled the prediction of the normal region with emphysema, whereas the end-to-end performed correctly. Another IEP subject showing that the end-to-end prediction was closer to the ground truth, so a better sensitivity and specificity. And also for a healthy subject, we see that the end-to-end did not introduce false positives. So in summary, the CNN model selected for the FIP was the UNet with the dice loss and cyclical learning rate schedule, which also allowed a whole lung volume analysis through slice-by-slice prediction achieved in a near real time. So this was an interesting result that allows further to apply this method to follow up, quantitative follow-up of IEP patients over time. This is an example of this kind of follow-up for a 2-year period at 1-year interval, showing the progression, the slight progression in this case of the diseased regions in blue, the emphysema region, in pink, the IAP. So with the advent of COVID pandemic, we asked the question if the FIMP model could be applied or used in COVID lesion detection. So for this purpose, we have retrained the model, this time separating between fibrosis and ground glass, the ground glass being more predominant in COVID. And in the resulting model showed a relatively good prediction of these classes with a slight overestimation, it's not very visible here, of the ground glass regions in normal areas, mainly posterior in the lung. We also took the advantage of a recent COVID challenge and we fine-tuned the model on the provided additional 180 CT data sets, this time acquired with variable CT protocols. And the fine-tuned model showed a better specificity for the prediction of the ground glass regions, but in some cases it shows an over prediction of the fibrosis part outside of the lungs. So because the two models do not share the same error, let's say, we are currently trying an ensemble model that combines both decision and which looks like performing much better in terms of ground glass prediction. Note also that in this model, the consolidations are considered as fibrosis and not a different class. This will be addressed later. And this could also explain that when consolidations are present in the scans, they are not predicted by the model. They are considered as outside of the lung. Otherwise, model seems to perform relatively well. So with these limitations in mind, we could apply this model to COVID patient follow-up in a current project. So this is an example showing a moderate case with depicting short time recovery where the lesions disappear after 3 and 6 months after patient admission. Another example shows a 9-month follow-up. This case, it's a severe case showing a longer time recovery and possible remaining of sequelae after some time. So to sum up, the AI model proved to be effective in assessment of type and extent of lung lesions. And the key factor here in the management of this kind of diseases remains a 3D quantitative follow-up. And this mainly impose to have access to CT acquisition protocol, which are controlled unless standardized. Further theoretical challenge to address are related to providing guarantees regarding the model accuracy and stability for a translation to clinical routine in multicentric clinical trials. And in terms of clinical challenges, the challenges are related to understanding the mechanism of progression, but also the regression of the disease, and to the prediction of the natural evolution or the therapeutic impact based on the CT biomarkers assessed in the early phase of the analysis. So this was the end of this focus talk. And I'll be happy to answer any questions if you might have.
Thank you, Catalin. This was perfect. You have 1 more minute if you wish.
Okay. Well, in this case, for 1 more minute, I can share this slide. For the next steps in COVID analysis, this will this will involve a vascular remodeling assessment in COVID. This is what we are currently working on. So looking how the vascular, the vessels in the lung are are changing over the time, and also there is another way to study the lung compliance using the polymechanical modeling with medicine teams in Polytechnique in INRIA. So this is also currently occurring in the INR project Silico Lung. So these are different paths to address CT biomarkers in COVID. So I think I'm done now.
Excellent, Catalin. Thank you so much for giving us such a rich presentation in so little time. As a reminder, if you have questions for Catalin or other speakers this morning, please use the Q&A function at the bottom of your screen to ask them. And next, we welcome Marc Lavielle, the Director of Research at INRIA and a professor at Ecole Polytechnique. Marc, do you want to share your slides? Yep, we see them. Yep, perfect. Thank you.
Okay, so thank you very much for the invitation. So I'm really very happy to present what I'm doing now, working on developing new algorithm for automatic model building, and I'm very interested in application in population pharmacology. So this is what I want to present today. So just a very short introduction to what we call pharmacokinetics modeling, or PK modeling. When we give a drug to some patients, pharmacokinetics consists just in studying, looking at what the body does to the drug, that is, how the drug is absorbed, how it is distributed in the bloodstream, in the organism, and how it is eliminated. For that, we have data, usually, we have pharmacokinetics data, and these data are just a plasmatic concentration over time, of the drug over time. So this is a typical kinetic pharmacokinetic profile for one patient. So when there is only one patient, the problem is quite simple, easy to understand. We have just some data, some longitudinal data, that is some observation at different times, at different time points. And we want to build some models, some regression model that will describe this profile. So here it's just usually a nonlinear model, which is function of time, and the model that we will consider depends on some parameters. And you will see that that's important. And we have, of course, some residual error that we need to take into account, to take into account the difference between what we predict and what we observe. So a modeler usually has some knowledge about this process. So how the dose is administered. It goes to, in this case, when it's an oral administration, it goes to the gut, and then the drug goes to the bloodstream. And when we consider what we call a compartmental model, we will consider that we have a central compartment where the drug is distributed in this case. Just a very, very simple example. So we need just to describe how the drug goes from the gut to the central compartment and how it is eliminated. So for that, we can have a mathematical representation of this model, and usually it's a system of differential equation, but I will not discuss at all about that. But this is something that is very classical in this field. So we can write an equation. So we know for a given pharmacokinetic model how to predict the concentration of the drug at any time. And then we just relate what we predict and with what we observe with our regression model. just considering that we have some residual error. And here you see that what is important is that the model depends on some parameter, what we call a pharmacokinetic parameter, which have some interpretation. The absorption rate constant, the volume of distribution, the elimination rate constant. So that's very, very important because that will really describe the kinetics that is observed. So this is for just one single subject, but in practice, when we consider a study, we have many subjects. Here, just some, 30 patients. And we have some data for each of these patients. And now what we want to do is to build a model, but a joint model for all these patients. So this is what we want to do. So here, the idea is to use the same pharmacokinetic model, that is here, in this case, the same system of differential equation. So we have, again, some parameters for this model. But the difference now is that we have different PK parameter for each patient. And this is how we will explain the difference of all this profile. These differences are explained by the difference in the PK parameter. So now this pharmacokinetic parameter are individual parameter, and they will consider as randomly distributed around some typical value. So we have now a joint model. For me, a model, it's a probability distribution. I'm working always in probabilistic framework. So we have, for each individual, we have a regression model, a nonlinear regression model. And we have a population distribution just to describe the distribution, the variability of the parameters of the model. So a model combines a in this case, a pharmacological model. It's really this structural model F, and a statistical model just to describe the variability of the data. And here we are in the classical framework of an incomplete data model, where we have two kinds of data. We have a variable, some observation, the PK measurements, and we have some non-observed variable, which are the individual parameters. And the challenge will be to build a model for the non-observed parameters, for the non-observed variables. So this is what we want to do. So a very widely used framework for this problem, for the population approach, is the use of what we call mixed effect models. So I will just say a few words about this model here. So here we consider, again, some longitudinal continuous data. So we have our regression model here. The residual error model also, we put some model here for the residual error, just to take into account the fact that the variance of the residual error can change over time. And for the individual parameter, we will use here a mixed effect model, and more precisely here, we will consider a linear model, a linear Gaussian model. That is, we assume that the parameter or some transformation of the parameters are can be described with some linear function of some covariates. And we have also some random variable, which are called in this framework random effects, which will describe precisely the difference between the random difference between individual parameters. And the transformation is very useful when we want to take into account some constraint. For example, if the parameters are known to be positive, then we will consider that the log parameter, for example, are normally distributed instead of the parameters themselves. Okay. And so at the end, we have this complete parameter, this complete model, sorry, and depends on a vector of parameter, which are the population parameter, the typical parameter, psi pop. We have some coefficient for the covariates in our linear model. We also have the variance-covariance matrix of the random effects, and some parameter related to the residual error model. And the problem now of model building is quite complex because there are many, many elements to define this model. So what the modeler has to do is to first select the structural model, and what is really the pharmacological model that better describe the kinetic profile, for example, which is observed. What is the form of the residual error? And also, he has to build on this linear model that is select first a transformation, what is the most suitable transformation of the individual parameters, what are the most relevant covariates that should be included in the model, and what is the structure also of the variance-covariance matrix. That is, are some parameters are fixed, so there is no variability. There's some correlation between some parameter. And this is really difficult again, because these parameters are not observed. So a classical approach for that is to use some information criteria, such as AKK or BIC, Bayesian information criteria, that is more generally penalize the likelihood approach. For a given model, we define the log likelihood of this model, and we just want to penalize this quantity. So, and this is a difficult problem because the model are nonlinear model, and it's extremely difficult to compute this quantity and the PDF of the observation. There is no closed form solution, of course. So for that, we need a powerful algorithm. It's very, very complex. So what the modeler does, he just selects a model, it fits the model to the data, then compute this criteria, and then try with another model, compare the results, and step by step try to improve the model by minimizing this quantity. So what we want to do, the aim of the algorithm that we have developed is to do that automatically and very, very efficiently. So first of all, we can imagine and we can think in an EM version for that, an extension of the classical EM algorithm for model building as follows. So if we, instead of considering our objective function or likelihood function just defined for the observed data, we can extend that and consider the complete log likelihood. And now also penalize on this complete log likelihood. And that's very interesting because typically this quantity is very easy to compute. It's much, much more easy than the incomplete version. And then the EM just consists at iteration k in computing the conditional expectation of this quantity. So given to the data and using the current model, and then just minimize this quantity. And it's easy to show that under very, very general condition, then the sequence of now information criteria that we want to minimize is a decreasing sequence. That is, we really improve our criteria at each iteration. The problem is that it's very difficult to compute this conditional expectation when the model is not a linear model. So we can think in some stochastic approximation of EM. That is what is called SAEM, for stochastic approximation of EM. And the idea is just to replace this computation of the conditional expectation by some stochastic approximation. And for that, we sample from the conditional distribution. So we sampled all the individual parameters from this conditional distribution. And now we have complete data which are available. And so we can now compute our criteria, our penalized criteria, which is now very easy to compute. So we can easily compute that and then maximize and to obtain a new model. So I will show a little bit more in detail how it works.
Marc, you have 1 minute.
Oh,
just for your information.
Thank you. So yeah, okay. I will move on. Just to say that when we consider a parametric model, the problem is we have developed an algorithm for that, which is called Samba. So I will not detail that, but it's easy in the sense that at iteration k, we just compute the maximum likelihood estimator of the parameter for a given model. Then we sample from the conditional distribution, and then using the complete data, we just update, we select a new model. And we have done that for many examples. This is just very quickly, just an example for PK data. And we find very quickly, in very few iterations, the optimal model. And you can see that it's extremely fast, and because for this problem, it takes about just less than 1 minute. But if you use a standard method for covariate model building, it can take several hours. So it's just to say that this is very efficient. It is implemented in Monolix, which is a widely used software platform for population PK/PD modeling, and it is also implemented in our package. So it's very efficient, as I said before. And now we are really very interested in extending its use for more complex problems, including, for example, application in pharmacogenomics, where we have a huge number of covariates. So any difficult problem is very welcome. Thank you. I'm sorry for being a little bit late.
No, you're perfect, perfectly on time, in fact. Thank you very much, Marc. Again, to our auditors, please send your questions to our speakers this morning using the Q&A function at the bottom of your screen. We will now discover our third research this morning, the research in robotics of Adriana Tapus, who is a professor at ENSTA Paris and the head of the doctoral school at IP Paris. Adriana, you may share your slides.
Okay, thank you very much. So this morning, I'm going to talk about challenges in assistive robotics and more precisely on long-term interaction, personalization, and trust. So it is very well known that large and growing subpopulations worldwide are suffering from a lack of trained and dedicated care. So in this context, the main idea, what we want to do is to build intelligent human-centered robots that can help people in their daily lives and continuously learn and adapt their behavior in order to provide a customizable interaction and help. So what is the motivation of this work, first of all? So socially assistive robotics have the potential to enhance the quality of life for broad population of users. And so we are talking about the elderly, individuals with physical and cognitive impairments, and those in rehabilitation therapy. However, such system pose a real and big challenge of being both population relevant and highly individualized to the special needs of each user in the particular beneficiary population. And this is due to the inter and intra individual differences and variability. So for this specific presentation, so I'm going to look to the user profile, because the user profile is really very important, and it was also mentioned earlier. And I'm going to look at it from 2 points of view. So first of all, so the psychological traits, which is maybe personality, and also from the physiological parameters, such as EEG, GSR, which is a galvanic skin response, heart rate, blinking, that have an impact on social interaction, and they are also used to measure the cognitive load. So with all this in mind, so we're going to explore the relationship between the user profile and the cognitive performance in different human-robot interaction scenarios, and also the personalization and adaptation of robots' behavior. So as previously mentioned, so in order to define the user profile, we look at 3 aspects from social sciences, which are the morningness and eveningness, a type of an individual that has a huge impact on the task performance and cognitive load. So it's when you say that you're a morning or evening person. So the personality of the user, so that influences the social interaction. And we also have the sensory profile of the users that defines the way the people are interacting with the environment and others. So through touch, taste, smell, movement, visual and auditory information. Of course, so this is not the goal of this talk, but just to show you what we are capable of, how we are capable of modeling the user state. So we can look at the thermal, you can see here, the thermal images, and we can recognize the emotional state of the user. We can also detect the GSR and link it to the difficulty of a task, and also detect the blinking rate of an individual, and the emotional state based on the gait and action analysis. So let me start with a concrete example where we applied our methods. And this was developed for the elderly suffering from mild cognitive impairment. So this work has been done in the context of the Horizon 2020 Enrich Me project. And so the aim of the project was to develop a personal robot for the elderly with MCI, and more precisely, to help the elderly remain active and independent for longer periods of time in their own home environments. So we had the chance to have 3 care facilities where we could test our system for long periods of time, so several months. And so we tested our system in Greece, Poland, and UK. So one of the main aspects that we focused on was the monitoring and recognizing the activities of the elderly in their homes. So while human detection no longer represents a big challenge, activity recognition is still far from being a solved task. And so this is mainly due to the fact that there are so many activities that people can engage in, and we cannot possibly consider all of them. So we wanted to see how accurately we can detect different actions of the elderly, and see if we can do the activity recognition in real time, and if performance of the system has an impact on the user trust in the robot's capabilities. So for that, we use the long-term convolutional network that it's used for a video input, and it comprises a CNN for extracting features in individual frames, and which are after passed to a LSTM network in order to extract the long-term dependencies. In order to, of course, one of the big problems is also to have data. We use half of the NTU dataset, which is one of the biggest dataset that exists today in the literature, which has more than 56,000 videos to illustrate 60 actions. And so we use this to pre-train our network. So these are the actions that we were interested for. So the elderly, so eat, drink, go to sleep, walk around, and so fall on the ground. So because we are working in a particular context, which is assistive application with the elderly, so some of the actions are not in the current existing databases, and they're not based, for example, on the vision. And so we had to create our also small own database with students and other people from the campus. Because, for example, we have falling on the ground. And in this context, we cannot ask the elderly to fall just for the sake of falling and just for us to be able to train our system. So we obtained a 54 successful recognition of the different actions and activities. And so from what we are working right now and what we are interested in is to investigate how the model can be adjusted to learn continuously during the interaction, also in an online manner, and how the feedback from the persons and the users could be used to improve the system in a case of misdetection. So another important thing that we had to face when we're working with the elderly, and here so you can see a person interacting with the robot, an elderly person, so is to see if they took their medication. So sometimes the elderly refuse to take the medication and lie to the general practitioner or to the user. And so here, so you can see here on the right, you see here an image of the face, a thermal image of the face of the user with the different region of interest. And so what we were interested in was for the robot to identify if it is lying or not to the general practitioner or to the robot. So we train our system on a limited set of data, and we inspired a lot from the forensic context in sciences, and we use different physiological parameters such as heart rate, skin conductance, space temperature, and also various behavioral manifestations. And based on this multimodal system, we try to detect lies. So we know, for example, that the heart rate increases to higher values when we lie, blood pressure sharply increases, skin conductance also increases to higher values, and the skin temperature increases in this periorbital region. So based on all this knowledge, so what we found is that like female participants had a higher heart rate when telling the truth compared to when lying. And individuals with high neuroticism had a higher heart rate when telling the truth than when lying. So all this information and all the data that we gathered, it's going to help us to create a model of and better improve our system for the elderly. So of course, there are many other things that we have studied in this project, and in particular for the elderly. But one of the most question that we wanted, and a research question that we wanted to address, is a trust linked to the performance of the system. So we saw, for example, for the activity recognition, it has only a 74% of successful recognition in real time. For the lie detection, it's also the same. So the system is not perfect. So a question that we wanted to know is the tolerance of the participants when the robot misdetects an action, and so the evolution of the trust in the robot. So what we have found is that communication is really very important for building trust between team members. And so we observe that decrease in trust when the robot fails to perform the task is lower when text and verbal interaction between the robot and the participant exist. So the trust at the end of the experiment was higher than the initial trust when verbal interaction communication is related to the task. So what we are really trying now to do is we are pursuing this, and we are trying to develop a probabilistic model of trust based on the performance and users' profile. So very quickly, I would also like to show another vulnerable and increasing population that is people suffering with sleep disorders. So various studies provide evidence that insomnia has a negative effects on physical and cognitive functioning, and more precisely on increasing the fatigue, reducing memory consolidation, and psychomotor performance. And it has, in general, a negative impact on the quality of life. So there are a lot of people suffering of insomnia that have car accidents due to micro sleeps. So what we want to investigate is just to see what is the impact of insomnia of the morningness and eveningness type in personality and cognitive performance. So and also how all these physiological parameters vary in order to be able after that to create our own model. So in order to do that, so we collaborated with a sleep disorder unit at the University Hospital Pitié-Salpêtrière in Paris. So we carried out some experiments that were part of a bigger clinical trial. So we had 15 participants. They were all outpatients of the department. They're all doing some kind of cognitive task and attention tests. So for all these tests, so we recorded the task performance and the data from the RGB and thermal cameras for blinking and facial temperature and GSR, but also the EEG and ECG data. So the first data that we had and that will help to create our own model is that insomnia influences task performance, but it's also dependent on the task. We found evidence that individuals with insomnia have a poorer cognitive performance than individuals without insomnia. Age is also an important factor. Some other things like sleep time was also associated with a low average temperature in the forehead region. So it is known also from the literature that higher difficulty level is associated with an increase in forehead temperature. Unfortunately, so this study has to stop due to the COVID-19 pandemic, but the idea is to learn from the users some of the parameters that have an influence on the task performance, so as to be able to provide a tailored intervention. So some of the challenges in assistive robotics for vulnerable populations. So everyone talks today about deep learning and learning in general, but in order to do that, so we need a lot of data. So this is really crucial. So popular data sets that exist today for automatic detection or recognition were not necessarily made with the elderly population in mind or other vulnerable population in mind. So just to give you some of ideas why they're different. So for example, we are doing emotion recognition from the face, but due to the wrinkles here on the eyes or the mouth, so it's harder for us to detect emotions. Also, some other, so there are differences in the prosody for the prosody analysis because there are differences in the voice. So you see, so there are a lot of aspects that should be taken into consideration. And for example, for the children with autism, which is another vulnerable population, so we say that they are so different, so that there is this huge variability, and there are no two children that with autism they are similar. So of course, so another big challenge is we are talking about long-term interaction in the wild. So the idea is to have this kind of robots in the environments for long periods of time, and also to provide a very encouraging and adaptive behavior of the robots. So just to summarize very quickly, so one theoretical contribution on the theoretical contribution stands for human user modeling, automatic incremental learning for human-robot collaboration and human-robot interaction, but also we developed the behavior control architecture that model, embody, and evolve with the user preferences and profile. From a practical point of view, we provided several customized therapies and monitoring for people with disabilities. So we work with the elderly, children with autism, people with stroke and insomnia. And with the whole idea is to have this improving the quality of life of vulnerable populations. So some of the future works, what we are trying to do is also to use generative adversarial networks for robot behavior generation based on user profile and actions. And also, as I said previously, to develop an online probabilistic trust inference model for human-robot collaboration and human-robot interaction, and also to see how the individual variability can be better integrated in the current models. Okay, so thank you very much for your attention, and if you have any questions.
Thank you very much, Adriana. I believe you have one question in the Q&A.
Okay.
To our auditors, please feel free to ask Adriana and other researchers your questions using the Q&A function at the bottom of your screen for those of you who just joined us. We'll now turn to our last presentation for the day by Gaël Varoquaux, the Director of Research at INRIA, who tackled the challenge of dirty data during his sabbatical and throughout the COVID pandemic. Gaël, the floor is yours. Perfect. We see your screen perfectly.
I need to unmute. Terrible.
There you go.
So, yes, I'll talk about electronic health records, and this will lead me into dirty data research. I'll start by setting the scene and discussing how we go from clinical studies to electronic health records. And to discuss a bit about clinical studies, well, the thing is they're really hard. Let's take an example of the COVID-19 vaccine. For instance, the Moderna vaccine took pretty much 2 months of lab development and then 8 months of clinical study on 30,000 volunteers for approval. And those clinical studies are actually still ongoing. It's pretty much the same picture for the Pfizer BioNTech vaccine. And so really the point being that experimentation on humans is difficult and it gives us slow cycles and high risks. And on top of this, we need to draw conclusions across individual heterogeneity. Real life evidence provides complementary evidence than clinical trials. So for instance, the question on whether vaccines prevent spread is not very well suited to intervention and requires huge sample sizes. And so this question was actually better answered in the case of the COVID-19 crisis from real-world observational data, specifically the Israeli data. That's the first answer we got. Basically following the individuals as they get or do not get the treatment. Now, this leads us to the source of data that we can use. And one of these sources is electronic health records. So patient records are basically anything you can get about individuals. So we're looking at claim databases, we're looking at in-hospital accounting, we're looking at the history of measurements on the patients, the doctor's notes. Now, this is really interesting because it may give us great longitudinal coverage. We may be able to follow patients through years and maybe even decades. For the Paris hospitals, the APHP, we're looking at 39 different hospitals that cover 8 million patients a year. So this is giving us great population coverage, also because this population is very diverse. We get people from different ethnicity, from different socioeconomical background. And on top of this is pretty much free data in the sense that this data is already acquired and we don't have an acquiring cost on this data. Now, of course, there are challenges, and the biggest challenge is that this data is extremely dirty. What do I mean by this? Well, the first glaring problem is that we have lots of missing values. So the data is acquired in a very uneven way across the different patients, across the different hospital sites. So for instance, we might have some data that is not measured, some specific features of an individual that is not measured because it's not applicable. For instance, some measure that you measure only on pregnant women. Or we're not measuring it because we don't have the sensor, or we're not measuring it because we didn't have the time in face of urgency. And here, I mean, on this kind of data set, we have a huge rate of missingness, much, much larger than in clinical studies. So typically we've observed often 80% of missing data or even more. Another problem is that we're dealing with non-normalized information. This is often due because we have manual input by operators, because we might have different conventions across the different hospitals. And so for instance, the same concept, diabetes type 2 mellitus, might be represented in many different ways, written differently, and to an expert, it's obvious that it's the same thing, but to your analysis, it's challenging. But the biggest problem of this kind of data set is it's actually observational data. There's no controlled experiment. There's no randomized intervention as in a clinical trial. And so as a consequence, you often have the case that treated and non-treated patients are not comparable. You might give, the treatment might be dangerous. So you might give the treatment more to young and healthy patients who have more chances of surviving the treatment than to old and sick patients. So we need to be careful with naive conclusions on treatment efficacy on such data. And now there is a statistical framework to answer those questions, which is known as causal inference. And just to give a bit of formalism, the settings are that you have a treatment, typically binary, 0 or 1. You have an outcome that you're interested in, but you have this idea of the potential outcome, which is you've got the observed outcome, treated or non-treated, but then this is the potential outcome. What would have happened if I had not given the treatment, or if I had given the treatment? And then you have the covariates, X, which basically capture the baseline condition of the patient. And so what we will need to be able to conclude on treatment efficacy is the notion of unconfoundedness. So basically, we will need the potential outcome to be independent from the treatment given the covariates. So the idea is that the potential outcome does not depend on whether the treatment actually got the treatment, whether the patient actually got the treatment or not. The chances of survival given the treatment or not given the treatment are independent on whether the person got the treatment or not. Now, this is by construction true in a randomized trial because the person gets the treatment randomly. And in observational data, we have to compensate for the baseline condition of the patient. And for this, we need to capture the link to the covariates. We need to account for the covariates to compensate the differences. And the two ways we can do this. The first way we can do this is that we can model the link between the outcome, the covariate, and the treatment. And this is a regression model. And we can learn this with an AI, which is basically statistical machine learning. And the other way we can do this is that we can reweight the patients, basically matching the covariate distributions between the treated and non-treated. So we're going to downweight young and healthy patients that got the treatment and downweight old and sick patients who were not treated. For this, we need to learn the probability of being treated given the covariates. Same thing, we can learn this with statistical machine learning. So the general idea is that machine learning can come into play in these analysis as non-parametric statistical estimator. And I'll show you that this is crucial because then we can start modeling the dirtiness of the data. So I've set the picture, and now I'd like to discuss two specific problems. The first one being learning on non-normalized data, and the second one being learning with missing values. And I'll take examples in a study of a salary given the employee position, because this is openly available data. And so we have this kind of data set. And the problem here is that the data is expressed with categories that are in non-standardized formats. And we like to call these dirty categories. This completely breaks classic statistical practice, which is sometimes called one-hot encoding, which means you encode each category differently, because we don't capture the overlap across categories, because we end up with huge cardinalities, because we have rare categories. So the standard approach these days is to curate the data. So we might do feature engineering to have a better data representation. We might try to merge entities. This is a standard task in database research, to output a clean database, for instance, to look at different entities that denote the same thing. Now this is feasible, but it basically requires supervision. It's really hard. Those two problems are really hard to make automatic and turnkey. So they basically take a huge amount of human time. Our view is that we can do supervised learning without this cleaning step, directly on the dirty categories. And we claim it can even be better because the statistical question at hand should inform the curation. So should we merge two different groups of a given entity, economical entity, or not? That really depends on the question at hand. So the first thing that we can do is simply to add similarities to one-hot encoding, to the standard practice. So we can add, for instance, string similarities, and we did this a while ago, and it really improves hugely the ability to capture statistical links. but it doesn't solve all the problems. One of the problems is that this kind of method, whether it's one-hot encoding or what we call similarity encoding, are prototype methods. But how do we choose a small number of prototypes? You know, we get in a huge number of prototypes when we do this. And at the end of the day, the right prototypes may not be in the training set because they might be relevant substrings of the data. So we're going to estimate the prototypes. Really, to do this, we can basically do string modeling and try to capture the relevant substrings. And in a huge number of data sets, there is actually this notion of relevant substrings. And so we're going to borrow techniques from topic modeling. So really the idea is that we represent the data at hand by its substrings. We are going to represent all the strings by a matrix that counts how many times it has given substrings. And then we can do matrix decomposition, so topic modeling, which is basically amounts to modeling those strings as a linear combination of recurrent substrings, okay? So we're inferring latent categories, and we're inferring what kind of substrings are present in a latent category. Now, if we do this, and we run this on data, what we really get is a representation of each category in the data as a continuous loading on latent categories. So we can really see that each category is represented as a loading, and we've this ladder method, so that this loading is sparse and hence easily interpretable. And as a consequence, we can do heuristics to basically assign feature names that are guessed to each of these substrings. So we can really say that we've inferred plausible latent categories. It's just that now our data is represented as continuous loadings on the latent categories. And I will be showing you the experiment results, but this works extremely well in terms of prediction. And here prediction is really capturing links, statistical links across the data. So we don't have to clean the data to do this. Given that this is quite useful, we're offering a software that does this, open source software, and it's basically a plugin replacement to, say, a one-hot encoder. And in practice, what we've seen is that if you combine this with gradient boosted regression trees, it works extremely well on tabular data. So now let me move on to missing values. So the problem with missing values is really that in some of the information, you don't actually have the information, you just know that the information is missing. Now, this is a well-studied statistical problem. It's related to incompletely observed models, and it's actually related to the presentation of Marc Lavielle. And really, the idea behind this is the way you can model this is that you have first a model of the complete data generating process, and then a random process that includes entries. This is the classical statistical framework. And there is a specific situation, which is known as missing at random, under which we hypothesize that the probability of missingness does not depend on the unobserved value. In this setting, there's a historical result that tells us that we can do basically maximum likelihood inference while ignoring the unobserved value. So this is very strong, and this is justification, for instance, for imputing the missing values. Now, the problem is that when we're not in this situation, the missingness is not ignorable, and we need a model of missing value mechanism. And just to set the picture, if we have the complete data here, missing at random is basically no strong structure in the missingness, and missing not as random, we have things like censoring processes, we have structure in the missingness. This happens a lot in real data, by the way, missing not at random. So we're switching gears, and we're looking at a different problem, which is not maximum likelihood inference. We're looking at supervised learning. Here we're going to be looking at risk minimization. And the challenge is that we're working on a half discrete input space. You know, missing is not in a vector space. And we can show that the best predictor ends up being complex, even in extremely simple settings, such as a linear model with missing at random. But there's some structure which we can capture. And if the way to understand this structure is that if we have a linear model, if the data are correlated, and if we get a feature that is suddenly missing, then we need to compensate by using the correlation to other features. So basically, when we're dropping a feature, we're compensating because this feature that that has been dropped is linked, is correlated to the other features. So when we do this, the problem is that we need different slopes for each set of missing features, but those slopes are related. So there's 2 to the D set of slopes, but they're related. So to cut a long story short, what we did is that we derived the theoretical forms for the optimal predictors. Then we approximated them with functions that are learnable by neural networks because they have the right structure, and we control the approximation between the optimal predictor and those functions. And then we built a tailored neural network architecture that is different from the ones that already exist, with a specific nonlinearity, which will learn all those slopes jointly by basically coupling all the parameters. And we call this the Numis network because it's based on the Newman approximation. And so if we do this, so we can show that theoretically it's consistent, it works well. And practically what we show is that we need less parameters and hence less samples to get as close as possible to the optimal prediction performance. And we compare this to wide architectures or deep architectures. So the structure needs less samples to approximate well and to predict well. And it's also suitable, and this is non-trivial, it's also suitable for missing not at random setting. And the reason it works is because it's based on empirical risk minimization. So to summarize, to take a step back, electronic health records open new doors for cheaper studies, but they're full of really complicated statistical problems. And AI, or actually machine learning, provides statistical estimators for these complicated problems or for the related information extraction. And we've studied precisely 2 problems, one which we call dirty categories, which is to learn with non-normalized data, and we have software for this. I think it's pretty ready for usage. And we're looking at the problem of supervised learning with missing data. And here the powerful result is it works also with missing not at random. And the bigger picture of part of this research is to do supervised learning without cleaning, accounting directly for the challenges of the data. Thank you.
Thank you very much, Gaël. Right on time. I really wish to thank our speakers today for sticking to the 15 minutes. That's pretty awesome, especially considering the richness of the research that you shared with us. It is now time for our panel discussion, and I will let Sylvain introduce our panelists today. Sylvain, over to you.
Thank you, Anne-Laure. I hope you can all hear me well. So good morning to all of you. I'm really delighted to introduce the second part of the webinar. And as Anne-Laure just said, I will start by thanking again all the speakers for these short but really interesting presentations and hopefully insightful on the variety of applications in healthcare we have in Paris. So now we're going to start the discussion part of the webinar, and before really jumping into the discussion, we will welcome 3 expert panelists. And so before the first questions, I'm going to introduce each of you, say a few words about our panelists, and maybe give you the opportunity to complement and add a few details on what I'm going to say, for instance, on the healthcare projects you've been working on the topics you're most interested in this webinar. So first, our first panelist is Harry Ecole. So Harry is a professor at Hôpital Saint-Antoine. He's a specialist of the role of the intestinal microbiome in immunity. And he works in the gastroenterology department at Hôpital Saint-Antoine. He's also the coordinator of the FHU PASEM, which stands for Paris Center for Microbiome Medicine, which gathers more than 50 teams, I think, working on trying to analyze the statistical behavior of microbiota. So welcome, Harry, and maybe you want to add a few words to what I just said.
Thank you very much, Sylvain. Good morning, everyone. Very happy to be here. So as Sylvain mentioned, I'm a physician, but also a researcher with a research team focusing on understanding the role of the gut microbiome in health and disease. And I have several types of interest, very, I would say, basic, fundamental interest in understanding the mechanism underlying the complex effect of the microbiome on host cells, and particularly in disease context, but also trying to use this microbiome as a therapeutic agent, but also as biomarker to predict phenotype, disease, complication, response to treatment. And in this context, we are working notably with Sylvain to try to apply AI to solve this type of question.
Okay, thank you, Harry. I hope we will have time to come back to this a bit later. Our second panelist is Théophile Mohr Durdez, who is a former student at Ecole Polytechnique and HEC. He's now the CEO and co-founder of Volta Medical, which is a startup or a young company which proposes software solutions based on machine learning and deep learning solutions to assist cardiologists. I won't say more because I think Théophile has a few slides to explain in detail what he's working on. Welcome, Théophile.
Thank you, Sylvain. Thanks to the Hi team for bringing me in. I'm glad to present. I don't know if I should present or if you are presenting my slides. I don't know. Should I share my screen or?
Oh yeah, you can. You should be able to.
Okay. That's So I am the CEO and co-founder of Volta Medical. Volta Medical is a company I co-founded 4 years ago with 3 physicians, 3 cardiologists in Marseille. We are now 35 in total with a subsidiary in the US. We recently raised additional funds, and our goal is to assist physicians and cardiologists in the EP lab, in the operating room, while they are operating patients in the frame of an intervention called ablation, catheter ablation. So I'll just say a few words about ablation and about what we are doing in the EP lab. So catheter ablation consists of introducing flexible catheters inside the veins and inside the heart. And then it's a 2-step process and intervention. The first step consists in measuring electrograms, measuring information, measuring real-time data. And after all these measurements and after understanding the arrhythmia, the goal is to ablate specific regions, pathological regions, to durably terminate the arrhythmias. And we at Volta Medical have developed a medical device. The name of this medical device is VX1. And we are providing assistance, real-time assistance during the operation to cardiologists to help them understand the arrhythmia and understand which specific regions are participating and contributing to maintaining cardiac arrhythmias. So we are basically guiding physicians towards the relevant regions for ablation. This device is CE marked. It's the first AI and deep learning based software to obtain FDA clearance in interventional cardiology. And we have validated this device in a clinical evaluation in a multi-centric study in Europe in 300 patients with 17 operators. And we have further investigations ongoing. And I just wanted to emphasize on a few things pertaining to this discussion. The first one is that I am still very closely working with physicians. So we are working with several hospitals in Europe to really understand the needs and the clinical context, but also build databases, test devices, test usability, to make sure that our devices and specifically VX1 fits within a clinical workflow. The second important aspect is the human-machine interface that was designed by electrophysiologists, and here again there are a lot of constraints but also challenges. And finally, we are working with a lot of regulatory engineers and quality engineers, and because all of this requires a precise definition of claims. So as we are working in an industrial context, we have to very carefully define our claims for the medical device, and also define the associated validation process that includes the verification of technical specifications, but also the validation of usability, and in the end, the clinical validation and the clinical relevance in terms of outcomes for the patients. So that was my brief introduction. Thank you.
Thanks a lot, Théophile. This will help us understand why you want the question you're going to ask to our researchers. And finally, our last panelist is Benjamin Farcy. So Benjamin had defended his PhD in numerical simulation before being a researcher at CNRS and Georgia Tech. And then he worked for a few years on modeling in multiple physics problems. He's now he joined Capgemini, who is a partner of SudParis. And he there performs data science consulting, and he acts as a data science manager. And since then, he worked in many projects, both in the industrial and academical worlds. But I think Benjamin also has a few slides to detail his work.
Yeah.
Welcome,
hello.
Benjamin.
Thank you. Hello, everyone. Thank you for all the presentations that were really instructive. And yeah, just a few words. So yeah, I'm working as a data science consulting at Capgemini, and I've been working with some of my colleagues on healthcare projects and various healthcare projects, and I just wanted to say a few words on those to show you what it looks like. Oh, share my screen again. So it's mainly in public sector, and this first one is to help the hospitals, also in Paris in a PHP, to modelize their patient flux. So especially during COVID. Basically, the inflow of patients in hospitals are what is like emergency in red, what is scheduled for operations, planned operations, and in blue, what was like the overload due to COVID. And there was a big work to model the flux of patients within the services in order to be able to forecast and to foresee the load of the patients during the crisis on a day-to-day basis, and be able to act on those scheduled operations in order to reschedule them or maintain them based on what was forecasted on the input of patients. So it really helps to manage the day-to-day situations and to take decisions on what operations should be rescheduled or not, in order not to have an overflow in the hospital. And so it's a solution that's currently used, and you see it takes the form of like dashboards on the KPIs that the users can see, can look at, and also scenarios that they can model to forecast what can happen and how they can anticipate that. This is one example. Another example is what's called Traumatrix. So it's a joint project with several other organizations, and it's similar in a way to what I just presented. It's how to best route patients that are traumatized when they arrive at the emergency services. So when there is a trauma, the first 24 hours, the first decisions are really important for the physicians and for the patient, and they need to take decisions really fast. And the goal of this project is to use data about the patient, about what is known already, to help the physicians take decisions and route the patient through the services. And one challenge also in that is how to use it in real life and how to validate the models. And what is a plan also, you see on the top right, is kind of an application in order to be able to collect data online on the way, in order to not only have like a model that has been trained and validated with closed data, but have a model that is constantly learning and constantly validated against real world data. Third one is more related to COVID, is through pandemic projection. There is a lot of available models that are made by epidemiologists in order to forecast pandemics. And basically, they are based on a system of numerical differentiation, so ordinary differential equations, and you can model populations through the pandemic. And what we did is a joint project with public sector, with a Grand Est region, in order to provide them a dashboard to be able to forecast and see the impact of the pandemic. So that's it for me for the presentation of the projects. And maybe I can begin the discussion with an introduction question.
Yes, sure. Maybe just before you ask your question, just to be clear with everyone. So the discussion, we can jump into the discussion now. There will be a few questions either from the panelists or from the Q&A. But this is thought as an open discussion. So even if the question is not directly targeted to you, if you feel that you've got anything to add or comment, feel free to open your mic and just jump in.
Okay, so I will try to launch the discussion with the questions, and you can jump on it. We saw a sample this morning of what AI and modeling can bring to healthcare through the presentation on radiography detection, pharmacology modeling, and also user personalization. Well, to me, there is no doubt anymore that AI can bring powerful solutions in the healthcare sectors. It's already there, and it's in research. But there's a lot of challenges for those solutions to really bridge the gap between research proof of concept and real integrated solutions in the workflows. And for me, from what I saw, one of the biggest challenges is to integrate those AI solutions in existing workflow in the hospitals, with practitioners, or in the industry. And for example, this morning we saw for Catalin how a radiologist can use integrated lung scan augmentation in the day-to-day workflow, how practitioners can use data modeling in the following of a patient individual care. With Adriana, a question could be how retirement home nurse can work together with cognitive detection tools, such as the one presented. And also with Gaël, how clinical study researchers can use data curation tools, such as the one you presented, to work with dirty data to leverage hospital data for their trials. So my question, to summarize to the researcher who presented and the other panelists, is how do you foresee the integration of those solutions you presented in real workflows? Also maybe more specifically to Théophile, that just presented VX1, and apparently you already bridged the gap. What challenges did you face in integrating this solution with the surgeons?
So maybe I can start answering. So I faced a lot of challenges. I mean, we faced a lot of challenges. I think maybe 20% of the work was research and the rest was bringing it to the labs. And the reasons are first regulatory reasons that are actually completely linked with scientific questions, meaning we had to very clearly define the device specifications and the claims of the device. This means not only the patient population and the intended use of the device, but also which type of device, which type of existing device it is compatible with, how we demonstrate compatibility. We also had a challenge about assessing ground truth. I think in the medical field, and this will be, I think, corroborated by the researchers today, ground truth is not unambiguous, and unambiguity is a luxury actually when you are looking at a classification problem. And this was our case. We had a strong level of disagreements between operators, especially in a real-time context of interpreting cardiac electrograms. And so we had to assess a ground truth. This was performed using basically a reader study. We had to have data annotated not only by one operator, but by several trained operators, understand the level of variability between operators, demonstrate that we were at the same, that we are reaching a similar level with our own device. So basically, I think there are regulatory barriers that are completely linked with scientific questions, but that also require a certain level of documentation and of quality inside the company. So it's not only about having a device that works, it's also about having a user manual that is perfectly written and fits the regulatory needs. It's about having a production process that works with labels, labeling issues, how you produce your labels, how you manage your providers, how you manage your distributors, so how you manage languages, barriers between countries, and cultural gaps. So basically, it's a kind of summary of the challenges, but I think it's about all what is beyond the device. So the device, but also how it is being used clinically, and how you can make sure that you don't introduce risk within usability. And maybe,
thank you, Théophile.
Maybe I had a question to Catalin on ground truth that is linked with your question, Benjamin. But how did you assess ground truth in lung segmentation?
Yeah, exactly. It's a big problem. That the ground truth is one of the problems that limits or delay the transfer of the solutions to the clinical practice. So in our case, the ground truths. So as I said, we could not have ground truths for the whole volumes of the CT dataset. So we have a sparse annotations, and these were in fact. We only have one expert radiologist and several junior radiologists. So that, and we also saw some disagreement between them. So in ideal world, I would say we will need several panelists, expert panelists, to annotate these ground truths. And we even with this the regions in the lung, the disease regions, are not so very, sometimes they are very complicated to delineate. So it's very time consuming to do that. So generally you might have some overall annotations that are not very precise, and this also might bias a little bit the network decision. So in our case, that's definitely a limitation, but we have to cope with it, because otherwise we cannot advance. In a recent challenge over COVID, that's in November last year, they had in their annotation data sets, if I remember well, they use seven expert annotators. So, but again, that data set was not as rich as we needed, in fact. So they have only binary annotation. They say, okay, COVID and non-COVID. So in order to fine-tune our model, for example, for this database, we have to transfer this and transform this database from binary annotations to labels that we needed. So yeah, in this case, I cannot say we had something that is completely validated by physicians. So yeah, it's something that join a little bit the presentation of Gaël with let's say kind of dirty data. So well, it's not so dirty, but it's sometimes could be a little bit inconsistent, and this is it's one of the problems of yeah, expanding these AI algorithms. But one possibility also, it's not looking at AI solutions as a one side of the solution that could be provided. So combining this solution with other classic existing techniques for extracting biomarkers, other types of biomarkers, and correlate all these findings with the biomarkers. Because yeah, in our current study, for example, there are other things to take into account. It's how normalizing the data that we have. So in the follow-up examples, I show that the patient, its own witness, in fact. So so it's more confidently to follow up a patient, knowing that it is his own witness for the disease progression. If you try to transpose it for multicentric studies with different acquisition protocols, so data are a little bit more or slightly different. It's more difficult, so you have to take care of drawing conclusions. So again, I think that the work of Gaël, it's very interesting in this point of view. Well, I don't know if I answer completely the questions, but we can continue talking about this.
So maybe if I can add something in terms of the question of implementing this type of tools in the real practice. I think that, of course, we need very precise tool to make positive diagnosis, notably when we are discussing radiology or pathology, basically pictures. We need positive tools to make positive diagnosis. But in real life, we also have to remember that physicians are prescribing tons of tests, a massive amount of tests. And one of the biggest questions is basically to sort out the normal results. And I think that in terms of implementation in the short term, what would be very helpful, notably for radiology or pathology, is just to give a tool to remove all the normal tests, pictures, and help the physician to focus on what is abnormal. If I give you a very simple example, when you are doing a CT scan for a patient, you are asking a question to the radiologist. You are asking what is aspect, for example, of the pancreas. I'm looking for pancreatitis. So the radiologist will focus his time, the short time he has on this question. And most of the time, he will not pay sufficient attention to the rest of the picture. And this is quite common that he missed something which is abnormal elsewhere on the picture. And I think that in this setting, having a tool just to detect what is abnormal, even if it's not a very precise diagnosis, would be very, very helpful.
If I may also, so some of the problems that we are encountering is that we are working with non-experts end users. So this is another aspect, and sometimes it's really very hard to to know everything from the start, how things are going to happen, how the interactions are going to happen. And so this is something that where the system need to incrementally learn from interactions and for long periods of time. And that means that the system also, and the learning system also, it's evolving. And this is become where the problem also becomes much harder. Also, so we need to deal with like learning in real time from human-robot interactions to know exactly what we need to learn, because it's not just one task. So if we are talking about social interaction, it's bigger than that. So so that's another problem. It's if we are introducing this kind of robots, social robots or assistive robots in the homes of the users, so the environment is not constrained anymore. So that means that we have domestic, unstructured environments. And that makes the problem even bigger, also for learning and for the social interaction. And these are some of the challenges that we are also facing.
Thank you, Adriana. I think, Gaël, you wanted to add something?
Sure, I just wanted to take a kind of a big picture point of view on the question and come back, and I've taken a few notes, and they're actually, somewhat going over a few things that have been said. But, if I go back to the original question, I see this partly as a change management problem, right? And I'd like to, selfishly say that my team is already in production in multiple ways. First, we did what I presented during the COVID-19 crisis 1 year ago, because it was needed. And there are lots of things to be learned from this, and I'll come back on this. But maybe the most important thing is that my team is part of the original developers of scikit-learn, so tool that is massively used. So we've kind of learned a lot from this. And when maybe what we've learned is you stick to simple solutions and you do them well. Maybe that's the most important message. But to come back to the bigger picture, there is clearly a validity problem. It's been mentioned by Theo, it's been mentioned by other people. And for the core validity, of course, we're not going to get around measuring whether what we do is useful or not. That's something, maybe that's something that's overlooked by certain more theoretical researchers. But at the end of the day, once we implement the solution, we need to measure the outcome. And so this, in medicine, this is usually done by clinical trials. We can also, clinical trials are very expensive. There's no way around them. We can also do part of the work by observational work to kind of weed out the things that don't work. So basically put our system in production, but not in control. Basically the system does prediction, but no action. But everywhere we do, we need a measurable outcome of interest to health. If we don't measure the impact to health, if we measure, the quality of prediction or something like this, the quality of prediction is not the impact to health. And we can have very good prediction, but slight biases that are actually detrimental to health. So we need an outcome, a health outcome. And that's classic of basically clinical studies. It's a difficult problem. But we need to, think about this literature. Then we have a big problem, which is the problem of acceptability. And I hear this problem. I've been doing this for many years, for more than 10 years. And basically what I've learned is that you need to show success. You can't go to people and tell them, my solution is amazing. You need to be able to demonstrate some success and to move one step at a time. And so for this, one thing that's well known in change management is that you need to target the easy wins. Because that's not what you're interested in. You're not interested in the easy wins, but you're going to go for the easy wins because you're going to be able to show success and then move one step at a time. And people will change given time if you give them evidence that this is useful. You can't, preach to someone a solution that person does not understand, telling him, this is good, trust me, that won't work. However, this is good. Look, I've seen progress before. This will work. And now you're going to hit one problem, which is the power structures, and that's something we've really hit. You're able to convince people, but some people have no interest in this change happening, and those people may control very high up the ladder. Now, that's a very difficult problem. And this is why it takes years, because you need to convince more and more important people. For the short story, we did many things during the COVID crisis that were undone after the first wave because some people had no interest in these things happening. And finally, something that has already been mentioned is implementation. Most of this is basically engineering and working on quality and not research. So we, of course, hate to think about this as researcher, but it's more important to have a basic solution well implemented than a fancy solution poorly implemented. This is another thing that we learned a lot during scikit-learn. And I like to say that people in research are often trying to move too fast. Sure, we're doing research because we're thinking about the future, but to push things in implementation, we need to take, kind of old ideas. And one last thing, and I'll stop there, is that we often misunderstand the application world. And it's fine, we're methods researchers, we're not health researchers. And for this, we need to work with health researchers to be able to understand this, to be able to understand where we're going to provide value. Thank you.
Thanks a lot, Gaël, for this very, very nice summary and lots of things to think about. Maybe I would like just to ask a question to Harry, or just to add one point on this. So, Gaël, you said first that clinical trials may be very expensive and hard to do to obtain proof on some outcomes, and also said that we should target easy wins. But maybe I'm wrong, but I think in your case, Harry, when you've got samples from the microbiotes, it's not this easy to select. Performing a clinical trial, you don't really know exactly which data are going to be useful then to predict any kind of disease first. And then it's for you, it's hard to target one easy win in this case, or would you find something that a statistician could find, or a machine learner there?
Yeah, so clinical trials are very, very hard, very expensive, very long to perform. And with, for example, with the COVID crisis, most of the clinical trials are basically stopped, except the one on COVID, of course. So clearly, I agree with Gaël, we need a new solution, at least to complementary solution with clinical trial to increase the efficacy of drug developments and strategy developments. In terms of using, for example, microbiome data to predict an event or to make a diagnosis, it can be, you can have very easy wins. For example, if you want to use a microbiome to know if a patient have an active inflammatory bowel disease or if he is healthy, it's very easy. You take the samples, you will have very nice signature. And I worked with some people trying to develop microbiome-based predictive signature on different diseases. And it worked very easily. But in fact, you don't need any tool to make the diagnosis yourself. You just need your eyes and you see that the patient has an active disease. So, of course, when you are dealing with clinical data sets or health data, I think it's very crucial to have the picture and the feeling of the physician, because if you are building a model that is basically useless because you don't need any tool to answer the question, this is a problem. And of course, if current tools or just the physician eye is not enough to make the diagnosis or to answer the question, most of the time, it's much more challenging, of course, to develop the tool. But what it means is that you need to understand the clinically relevant questions that you have to address, and not only to take the hanging fruits that might be very easy to model, but might be also completely useless.
If I may intervene here, so I don't know your specialty, but I think you mentioned something that was quite interesting before talking about radiology. You mentioned that basically beating a trained radiologist to answer a specific question was extremely hard. But you also mentioned that, you know, a very much lower quality screening technique could be very useful basically to avoid missing incidental findings. Now, I know nothing about microbiome, but the question is given your current practices, you know, helping you with your current practices is going to be extremely hard. Now, can we rethink practices? Can we, because can we basically shift completely the practice and shift the cost of the different operations? And so to enable new practices, where in no way in those new practices, any AI is outperforming what you do.
Not sure I get your question. Not sure I get your question.
Well, my question might be misguided because doing the sampling of the microbiome might be very invasive and hence dangerous. But my question was, if we the cost of the cost of a physician time is not tiny. So now, if we were to remove completely the cost of a physician time, but to provide lower quality results, would this enable another practice that is not currently done?
Yes, this was actually what I was meaning by having tools to basically filter the results of the test. So again, currently we are prescribing, we physicians globally in the world are prescribing tons of radiology-based tests. CT scan, but also very simple chest X-ray and MRI, and tons of it. Most of it are normal. And despite this, you have trained radiologists, you know, 10 years of training that spend time to look at this picture one by one. So it's a massive waste of time from my point of view. And if we can have a very simple tool just to remove half of it, for example, even if it's not perfect, if you just remove 30%, 40% of it and say, okay, this is normal, you don't have to look at it, that would be very, very useful. And the second aspect would be just to detect something which is just not normal, even if it's not a precise diagnosis. As a first step, in the next few years, I think it would be much more useful to get a tool that tells us something is happening here on this chest CT scan than to have a very precise diagnosis on the, for example, on the type of cancer or so on. Because then the radiologist can take the necessary time to focus on this abnormal picture and make the appropriate diagnosis.
Thank you, Ari and Gaël. This gives us a few things to work on to get easy and quick results, even if they are not perfect. So maybe a question which is suggested by Anne-Laure, which is kind of a follow-up to this. So in the idea of bridging the gap between real applications and what comes out research labs, is that we are all more or less involved in some teaching in our schools or departments or labs. And it seems that the engineering schools and maybe the medical application maybe are far apart for now in the way we teach models and statistics models, machine learning. Would you have ideas now on the way we could accelerate the adoption on AI tools using teaching on the way we teach to our students?
I just want to plug that we're going to open a MOOC online course in a few months that is really going to be aimed at teaching machine learning with Python to people who have no specific mathematical background.
So you've got a solution.
Well, the question is more precise than that. So a MOOC will certainly help out. The question more specifically in healthcare is we have very busy experts We have sometimes nurses and, not necessarily surgeons only or highly qualified doctors using the AI. And the question is very general. What's the best way to diffuse the AI solutions that we develop at HiParis? Is it, for instance, something that should be taught at HiParis, or should we change the curriculum in medical school, for instance, or should we bring nurses in large groups over to our campuses to train them? How do you see that change happening over the next few years?
Well, I think we shouldn't be too naive about the world. So I studied physics. I didn't study math, but after my physics study, my knowledge in statistics was peanuts compared to that of a biologist or a psychologist. So I think we shouldn't, sure, we can evolve the curriculum of med schools. I don't know for nurse schools, but also we need to be a bit humble and realize that the curriculum is not that bad, and our tools are sometimes just not right for for usage.
I think that it's more question of culture than really of knowledge. I think, I'm doing basic science research, but many of my colleagues who are doing research and who are physicians, they don't have a very deep knowledge about basic science, but they still have some kind of culture about it, meaning that they can have a dialogue with the scientist. And I think that's the most important aspect. And probably this should be done in both ways. Engineers should have some kind of culture about medicine. And on the other hand, medical students should have some kind of culture about machine learning and all these type of tools.
So if I may, I think that like more collaboration also, so an open kind of collaboration, because we are not aware of everything that is done also in the hospitals and all the, so that's also about sharing, so the knowledge. So there are a lot of things that are already going in the hospitals, and we are also trying to develop new things from the academic and more scientific point of view. And I think it's just like kind of bringing them together, which is the point that it's really missing today. And I think so this is where we should go, because I know from my point of view, usually it's the other way. So we are going as scientists, we are saying, okay, I have some kind of tool, and I will go to see so the medical stuff. And so usually they're not coming, or very like small amount of practitioner are coming in asking help, so, or tools. So I think we should find a solution to bring the communities more together and have this kind of sharing of what we are doing.
And from the physician perspective, I can tell you that it's true. On the other hand, most of physicians who are doing research just don't know where to go so it's really going both ways.
Alors, wouldn't be a form of going forward, having a, for instance, a AI learning hospital? Would that make sense? Where all AI recently developed tools can be accessible to doctors, made available, and just so that at least the medical community is aware that these tools even exist?
I don't know if this is really the question of the tools, because of course, having very, easy to use tools such as scikit-learn or others, it's very important, but it does not make you an expert. So I think it's more to have the knowledge about who is doing what and who is open to work on what type of field. So it's much more putting people together, I think.
I completely agree with Harry. Having worked 4 years with cardiologists, not only with my associates, but other cardiologists in the world, they are really, most of them are eager to propose subjects. Most of them would like to start an entrepreneurial project or simply a research project on a specific topic that they would like to cover. They would like to work with engineers. They would like to, but the issue is they don't have access to engineers, or at least they don't have an easy access or easy understanding of whom they should reach out to. And so I think it's more about reaching out to hospitals, reaching out to physicians to tell them we have students that we are going to make available for specific medical research projects that you can propose and suggest, and this way people can just gather, and it's really key to have the involvement of physicians in such a project. They are instrumental at each and every step of the project, being it the very start and the specification until the clinical study design and the clinical understanding. I mean, it's a must-have. So I think it's about more reaching out, and I agree that the tools are maybe not the right way to see this issue.
Like in a more practical way, we can maybe also ask the health practitioner also to have some kind of like proposing internships or some of the questions that they may have, and that maybe our student can solve their problem, or maybe not one student. So also like collaboration between a medical student and engineer students that can work together, because they are not talking necessarily the same language. You know, so sometimes engineers and so that's just like bringing together, maybe not necessarily from small projects. First of all, just to be aware of what we are doing and everyone that's what's doing. And I agree that it's not necessarily the best thing, like showing just the tools, because what the tools that we have developed, they're already there, or like they were thought with some kind of health practitioners. So, but we are capable of doing much more if we know what are the needs. So this is also something that we have to be aware. So I'm sure that the medical staff they have more needs, and we can also propose solution, but we are not aware of all the problems that may occur.
This is really coming back to defining the unmet medical needs. And because, of course, everyone, we must work on questions that are real. So we need, and when I say we, I mean you need to know what type of question are relevant. And there are tons of it.
And there are also tons of non-relevant questions.
Yeah, of course, much more.
Much more, actually.
So I've learned a secret weapon recently, and it's an actor I've not heard about in this talk. It's basically the public health professional, or biostatisticians. And so basically hospitals, especially clinical research, are full of people who are quite qualified with statistics and who are MDs, medical doctors, or who understand the applications. They're called public health doctors or biostatisticians. And I recently have started talking much more to these people, and I find it extremely interesting because they can basically bridge the gap, because they are often very expert about one specific field of medicine, but they can really understand my statistical talk. Now, there's one danger is that they've been trained, maybe 10 years ago, 20 years ago, and they understand statistics very well, but maybe not the tools I'm using. And so there is one danger of basically sociology of change, is that if we come in a non-subtle way and basically threaten to replace these people, then they'll act against us. Now, if we come in as ally to these people and basically show that we can speak their language and empower them, and not, or trying to short them with a relationship with the specialist, then we can have allies.
I think they are really not doing the same thing.
They can bridge the gap. They can,
yes.
Talking, basically, it takes me much less time to talk to a public health specialist about, specific application, whether it's cardiology or anything, than to talk to the cardiologist. Because to talk to the cardiologist, I need to transform the problem. I need basically to understand the whole pipeline of cardiology. Whereas when I'm talking to the public health specialist who actually knows cardiology very well, that person bridges the gap.
Yeah, but the problem is that you don't have a lot of these people with an expertise on a specific disease. You will have some, but it's not generalizable. That's what I mean.
Yeah, from the clinical side, it's also a culture shift. As Harry told. So currently, that there are formations for masters that put together physicians or intern physicians, intern students, and engineer students that form them for a master too. And these new practitioners will be much more open-minded towards these AI tools. So they will know the capability, so it will be much more inclined to use them and to accept these tools and promote these tools in their future services. And this, I think this is one possibility to continue this exchange and mixed between engineering students and physicians that work on healthcare problems
Thank you all for this really nice answers. We have a question in the Q&A about the usefulness of explainability for physiologists, and maybe I would like to complement by asking about uncertainty. So maybe it's related to what Gaël and Marc presented. So Gaël, you talked a bit about under which assumption we could consider data to be missing, and then to explain how we could deal with it. Marc, you propose a few models, a way to select models with assumptions on the way, on the conditional distribution of missing data given observations. That these models help understand the uncertainty in the predictive prediction we make with these models. So is it possible in practice to design a really nice quantification of uncertainty? And is it useful for practitioners? So maybe this part is more for Harry, I don't know.
Marc, I'll let you start.
So the first question was about explainability. So
yeah,
so
explainability for the first question, I think that of course it's always nice to understand. It's always nice, but we have to admit that in medicine, most of what we are doing, we are not understanding what we are doing, at least initially, and even when we built new drugs that are supposed to be very targeted on specific molecules, we see a nice effect and we are very happy, say, okay, this is coming from a precise hypothesis, it works the way I want. Many times, few years later, you discover that it's not working at all the way you think. So for the physicians are really pragmatic people. They want to help their patients. Even if they don't really understand how it works, this is okay.
Well, thanks, Harry, for this really interesting answer, because I've been working with a psychologist for 10 years and also with physicians. And my experience is pretty much this, is that psychologists always want to understand. And by understand, it means make a very, very simple model that can fit in the head. Physicians, they really want, clean demonstration of positive outcome. It needs to be clean, it needs to be robust. And understanding is about building trust, basically, is I'm going to give you some black box that you don't understand. Why should you trust me? And it kind of loops back to your question on uncertainty characterization, which I think is extremely important. And it's not only important in healthcare, it's important in most of the applications where you're going to do an automated decision and then, have an operational logic on this. Depending whether you trust your prediction or not, you're gonna have different operational strategies on this. And there, I'd like to say that my classical toolbox, which I use, which is empirical risk minimization, which is that of deep learning and of modern machine learning, actually does not shine. And the tools that Marc uses, which are more probabilistic modeling, tend to work better. There's a really interesting research question here.
So globally, in the mind of physician, it's always nice to be able to have a kind of history about what you are doing, even if it's not really precise and defined. However, I fully agree with you, Gaël, is what the physician wants is a hard proof of efficacy. And this is joining the outcome question. We need to have hard outcomes. The precision of the test is, of course, very important, but what we need to show is that it is helping the patient at the end.
And this is not only important for truth and for science, but also for science, for finance. If you want to have reimbursement, if you want to have the administrators of hospitals pay for the device you are offering, you have to have clinical data, strong clinical data, and this is a step-by-step process, like Gaël mentioned, and this is also a very costly and long process, but absolutely necessary. I agree.
Thank you all. So just to follow up, we have a few more minutes. We're close to the end. Maybe a question which is specifically targeted to Catalin, and something that may interest you, I guess. It's to what extent we can generalize a model which can be used in a large variety of applications in healthcare and large variety of data acquisition protocol. So you design a model, for instance, in your case, you designed a way to detect some lungs issues. You did it using a specific protocol, a specific model, which you then tuned. So you fine-tuned, you process the data specifically to make it work. And then I get, in an ideal case, you would like to use it in many other situations or the same ideas. So do you have an idea on what is the best trade-off between a very specific model, which is really efficient in your application, and a model that could be generalized to many data acquisition protocols onto other diseases, for instance? I guess you face it specifically, but I guess you're not the only one here.
I think it's a general problem. Yeah, if ideally we would like to have a model and develop that works for a large variety of data sets, and in the real life shows that in different clinical settings the data acquisition is not the same, the protocol are not the same, and even for the same type of studies you might have difference in protocol. So I think, yeah, ideally having a model that works and that fit all these data variability, would be fine. But I think it's much more difficult to get it. So probably one way to overcome this issue is to have a model that it's able to well perform on a smaller variability of data sets, and impose and adapt the protocol, the clinical protocols for specific types of clinical research or clinical problems. But the thing is, you can do that with the condition not to change the way of working at the hospital side. So you can eventually ask for this type of study, for example, in the lungs. If you want to have a good prediction and a good follow-up of the patients, you should use this kind of protocols, even if you don't have exactly the same scanner machine or the same habitude to work. But if you will ask changing completely the way of working, I think this will be a problem. So the thing, it's probably the trade-off. It's to have models that are able to work on data with some variability anyway, but with a control acquisition protocols in a certain amount of control that is acceptable on the clinical side. So what we see in the current challenges that are done even in COVID. So the data sets that are provided are very large, with protocols which are completely different. The image quality is completely different from one side to another. But yeah, this is, I think, for challenging the participants to provide a solution that will work for all these data. So, and sometimes what we see that the solutions that are obtained are not really working on completely on this data. But if you just reduce the variability of the data, if you are able to focus and to control the acquisition protocol, you achieve much better results with different models. And the models can be also be designed to adapt to the acquisition protocol. So have a separate model that are trained or work on ensemble of models that can be trained or weighted to produce the output result according to the type of the data that you are facing, that you are encountering in a specific center.
Thank you, Catalin. Does anyone else want to add something, or fine? Sounds good. So it's exactly 10. So perfect answer, Catalin. This was really great timing. So I would like to thank all of you very much for being here, all the speakers and panelists. We already lost Benjamin and Harry, who had to go a bit before the end, but we will transmit all questions you could have to them if needed. So thanks a lot to all of you. If you have any questions or any comments, feel free to contact Anne-Laure and myself. We will be happy to answer and to give you context if needed. And if you've got any project or any things related to healthcare that you would like us to look at, we'd be more than happy to help. So if you've got anything else to add, thanks a lot to everyone, and have a good day.
Thank you, everyone. À bientôt.
Thanks a lot. Thank you.
Au revoir tout le monde.
Thank you. Bye.
Bye.
Goodbye.
Bye.